This video is all about hyperbolic identities. So we've already proved one hyperbolic identity. I did this in video, I think it's the first video actually, so I'm not going to go through this in detail, but here we are proving that cosh squared A minus sinh squared A is always going to be equal to 1. So just look through that proof, make sure you're happy with it. If you need further explanation of that, do go back and watch video 1 where I did this one. Right, let's do a new proof. Let's prove that sinh of A plus B is equal to sinh A cosh B plus cosh A sinh B. That should look very familiar to you. Let's go through it. So sinh A, we can write that from its definition as e to the A minus e to the minus A over 2. Cosh B, we can write that as e to the B plus e to the minus B over 2. Plus cosh A, we can write that as e to the A plus e to the minus A over 2. And then finally sinh B, we can write that as e to the B minus e to the minus B over 2. So this is me writing out the right-hand side. Right, let's multiply out these brackets. So I'm going to have a 4 on the bottom of both of the fractions. Right, e to the A times e to the B is e to the A plus B. E to the A times e to the minus B would be e to the power A minus B. Then we've got minus e to the minus A times e to the B, which is going to be minus e to the minus A plus B. And then finally for the first set of brackets, minus e to the minus A times e to the minus B is going to be minus e to the minus A minus B. Next set of brackets, I'm going to have, I'll do this one a little bit quicker, e to the A plus B minus e to the A minus B plus e to the minus A plus B minus e to the minus A minus B. Now, I've expanded those brackets and I've got a common denominator of 4. I can add these two fractions together. So I've got e to the A plus B plus e to the A plus B is going to be 2 e to the A plus B. E to the A minus B minus e to the A minus B, they're going to cancel out. Minus e to the minus A plus B plus e to the minus A plus B. Again, they're going to cancel out. And then finally, I've got the minus e to the minus A plus B, minus A minus B, and I've got another one of the same over there. So I've got 2 lots. So I can say minus 2 lots of, now I could say minus A minus B like that, or I could factorise that minus outside, like that. Now I'm going to cancel out these 2's, and I've got e to the A plus B minus e to the minus A plus B all over 2 which is, by definition, the definition of sinh. I've got sinh of A plus B, which is the left-hand side. So that's proved. We could do similar things with the other addition formulae to get these things. Again, these should look very, very familiar, but maybe with a slight twist or two. Let's do one other proof, and then we'll talk about how these link together with the trigonometric identities that you're already thinking about, I'm sure. So we want to prove that Cosh 2a is identical to 1 plus sinh squared a. So let's start on the right-hand side. I've got 1 plus 2 lots of sinh, so that's going to be e to the a minus e to the minus a all over 2 squared. My sinh a squared. Expanding those brackets, I'm going to have e to the 2a minus e to the a times e to the minus a, but there'll be 2 of those. And then I'll have a plus e to the minus 2a. And all of that is over 4. These two terms here in the middle will cancel out. So I will have 1 plus 2 lots of the e to the 2a plus e to the minus 2a, and I've got that minus 2 still on the inside there, all over 4. I'll take that 4 outside here. So the 2 over 4 is the same thing as a half. Multiplying out that bracket now, I've got 1 plus a half of e to the 2a plus e to the minus 2a, so all of that is halved. I'm just halving all of that in one go. Half of the minus 2 is minus 1. We can see the plus 1 and the minus 1 cancel out, so I just get left with e to the 2a plus e to the minus 2a over 2, which is, by definition, cosh of 2a, which is equal to the left-hand side. So we've seen some familiar looking identities, and we've seen some different looking identities. I just want to talk about the difference between them, because there is a rule we can use here. So first of all, the ones at the top. You can see in for all of these, I've written the trigonometric identities in purple and the hyperbolic identities in black. And we're looking to see what's the same and what's different. So the trigonometric identity, sine a plus or minus b. So we've got a plus minus here, we've got a plus minus here. For the hyperbolic identities, plus minus here, plus minus here. Everything else is exactly the same. This trigonometric identity is exactly the same as this hyperbolic identity. Let's look at some of the differences. Let me just clear that highlight off. So we know that the classic trigonometric identity is sine squared plus cos squared is 1. But the hyperbolic identity doesn't have a plus there, it has a minus. It's a cosh squared a minus sinh squared a. So the sign has flipped. The identity, the addition formula for cos, when we're dealing with trigonometric functions, When that's a plus, this is a minus. When that's a minus, this is a plus. So the signs flip for the trigonometric identity. But when we're looking at the hyperbolic signs, they stay the same. So in comparison to the trigonometric identity, the signs have flipped. And then the other one we just saw, the cos double angle formula, is usually 1 minus 2 sine squared A. But we just proved a moment ago that with the Cosh double angle formula, we have 1 plus sinh squared A. So notice how these signs are flipping. And what is it that's common about all these examples at the bottom that is not common about the ones at the top, where that sign flipping does not happen? It is the it's the sinh. Here I have I've got sinh squared here, which is 2 sinh being multiplied together. Here I have a sinh A times a sinh B. I have 2 sinh being multiplied together. And then down here I've got sinh squared A. I have 2 sinh being multiplied together. Whereas in the first case, where the signs were the same, I had a sinh times a cosh and a cosh times a sinh. I didn't have any sinh being multiplied together. This is called Osbornes' rule, where if you have a trigonometric identity, so something that you know you've been using in A-level maths over and over and over again with trigonometric functions, you can write down the corresponding hyperbolic identity where you replace the cos with cosh and you replace the sine with sinh. But if you have 2 sinh terms being multiplied together, you have to flip the sign. So basically, if you've wanted to swap a trigonometric identity for a hyperbolic identity, then all you do, you swap the cos for cosh, you swap the sine for sinh, that's all fine, but you be super on the lookout for if you have a sine, a sinh times a sinh. If that's the case, you have to swap the sign. That is also the case if you have a tanh times a tanh. Because remember that tan is the same thing as sine over cos. So if you have a tanh times a tanh, then that is also a sinh times sinh. It's just hidden away within the tanh. So let's look at a couple of examples of how we can use Osbornes' rule to write down hyperbolic identities without proving them from scratch. So I know a trigonometric identity is that cos 2a is the same thing as 2 cos squared a minus 1. So I could also say that cosh 2a is going to be equal to 2 cosh squared a minus 1. I'm just simply swapping the cos for cosh, the cos for cosh. There is no sinh times sinh in this whatsoever, so I'm not changing any of the signs. It's just going to be exactly as the trigonometric function is. Next, the tan A minus B. From our work on trigonometry, we know that's the same thing as tan A minus tan B over 1 plus tan A tan B. I'm going to write down the hyperbolic identity that matches up with that. So tanh of A minus B is equal to tanh A minus tanh B. That's all the same. Again, there's nothing being multiplied together yet. But then notice here I've got a tan A, tan B. And within that has a sine times a sine. Because of that, because of this sine times sine here, I am going to flip this sign to be a negative. So it's going to be 1 minus tanh A, tanh B. So this is how we can convert trigonometric identities into hyperbolic identities. We're now going to have a look at a few examples using these. So this question here, we're told that sinh x is equal to 3/4. And we want to find the exact value of cosh x, tanh x, and sinh 2x. So for cosh, now I know that cosh squared x minus sinh squared x is always equal to 1. Therefore, I know that cosh squared x minus, now if sinh x is 3/4, then sinh squared would be 9/16. I can add the 9/16 to both sides. And square root to get plus or minus 5/4. But I do know that cosh is always positive. Remember, it's always bigger than 1. Remember our graph of cosh? It's always bigger than 1. So that means I can get rid of that negative. B, tanh. Well, remember that I know that tanh will be sinh over cosh. Sinh was 3/4, cosh was 5/4, so I'll get 3/5. And for C, I've got sinh of 2x. Now, I know a trigonometric identity. I know that sine 2x is equal to 2 sine x cos x. So I'm going to use the equivalent hyperbolic identity. Sinh 2x is going to equal 2 sinh x cosh x. There is no sinh being multiplied together with another sinh. So I don't need to flip any signs. And so I can just say it's going to be 2 times 3/4 times by 5/4, which is going to be 15/8. Now, just to finish off this video, we're going to look at some equations to solve. This first one won't need any identities, but the other ones will. So this first one says solve 6 sinh x minus 2 cosh x equals 7. Now, we don't need any identities because we can turn the sinh quite easily into e to the x minus e to the minus x over 2. And we can turn the cosh into e to the x plus e to the minus x over 2. If I expand out those brackets now, I'll get 3 e to the x minus 3 e to the minus x minus e to the x minus e to the minus x. Then collecting up some like terms here now. I'm going to have 2e to the x minus 4e to the minus x equals 7. I'm going to rewrite this as 4 over e to the x, so that it's a bit more obvious that I'm going to multiply through by e to the x. So multiplying through by e to the x now, I'll get 2e to the x times e to the x is e to the 2x. Minus 4 equals 7e to the x. Move everything onto one side. And we can either make a substitution here, or I think this is going to factorise quite nicely. This is going to have to be a minus 4, and that's going to have to be a plus 1. So either e to the x equals minus 1/2, which it can't be because we know e to the x is always positive, or e to the x equals 4. So therefore, take logarithms of both sides, x equals ln 4, which is 2 ln 2. So that was a reasonably simple hyperbolic equation to solve, because we could just use the identities, just use the definitions of sinh and cosh straight away. This next example, you can see we've got 2 cosh squared x minus 5 sinh x equals 5. So I am going to change this cosh squared into a sinh squared. Remember that cosh squared x minus sinh squared x is equal to 1. So therefore, cosh squared x is going to be equal to 1 plus sinh squared x. So I'm going to replace that cosh squared with 1 plus sinh squared so that it matches up with the sinh. Just bear with me. Right, okay, so I've got 2 lots of the cosh squared, so 2 lots of the 1 plus sinh squared. Minus 5 sinh x equals 5. Expand the brackets and move everything over to one side. I get 2 sinh squared x minus 5 sinh x minus 3 equals 0. I can factorise this quite nicely to be 2 sinh x this is going to have to be a plus 1, and that's going to be a minus 3. So either sinh x is going to equal minus 1/2, or sinh x is going to equal 3. So therefore, x will equal r sinh of minus 1/2, or r sinh of 3. And we can use the definition of r sinh that we saw in the previous video. Remember, r sinh x is equal to ln of x plus the square root of x squared plus 1. We can use this to actually work out these values. So for the first one, substituting minus 1/2 in here and here, I'll get ln of minus 1/2 plus the square root of 1/4 plus 1, which is going to simplify to be 5/4. And I could then simplify that further to be so ln of, so the 5/4 will become root 5/2 when I square root it. And obviously I could then bring those two fractions together because the common denominator is 2. Or working out the answer that corresponds with the r sinh 3 now. X equals ln of 3 plus the square root of 3 squared plus 1, which is just going to be that. So these are my two answers for solving that equation. Okay, last example. It's a long video, I know. Right, we want to solve cosh 2x minus 5 cosh x plus 4 is equal to 0, giving our answers as natural logarithms. So notice that this is a double angle, that's a single angle. So we need a double angle that involves, we need an identity that involves cosh 2x. Well, I know that cos 2x can be 2 cos squared x minus 1. So I'm going to use the equivalent for cosh. Cosh 2x is going to be equal to 2 cosh squared x minus 1. I don't need to worry about any sign flips here because there is no product of signs involved. So I've got 2 cosh squared x minus 1 minus the 5 cosh x plus 4 equals 0. Collect up the like terms. And factorise. Nope, that doesn't work. That's not correctly factorised. Bear with me. That's going to have to be a minus 1 and that's going to have to be a minus 3. Yep, that will work. So, either cosh x is 3/2 or cosh x equals 1. And again, using the let me rewrite it first. So x equals r cosh of 3/2 or x equals r cosh of 1. Remember that the r cosh formula from last lesson was ln of x plus the square root of x squared minus 1. So substituting 3/2 into that, we'll get ln 3/2 plus 3/2 squared minus 1, which is going to simplify to be root 5/2. Or if I substitute 1 into that, I'll just get ln 1. It's going to be ln of 1 plus the square 1 squared minus 1, so all that's ln 1, which will just be 0. Okay. So there we go. Those are the two solutions for, well, 3 solutions, because we got the plus minus there. This will be a positive answer. So there we go.